Okay, so we're going to continue our discussion with stoichiometry. This is something that we studied back in chemistry, and back then we used BCA tables, which were before-after change tables, if you remember correctly. Our first example here is going to start off with methane, and I'm going to rewrite the equation here so that we can work with that in our BCA tables. First step is to make sure that your equation is balanced, which this one they've already done for us. Okay, then we're going to calculate the mass of oxygen required in order to produce 2.23 grams of carbon dioxide. So we want to be able to this is before, change after. We want to finish here where we've made 2.23 grams. Remember, with BCA tables, you cannot put grams in the BCA tables. You need to make sure that the material that you have in there is either liters for gas volume, or you have to have it in moles if you're dealing with anything else. So just keep that in mind, that kind of rule. So we've got to, before we can work with this, we have to be able to convert this grams into moles. So I'm going to multiply this times, I'm going to divide this by 44, because there's 44 grams per mole for carbon dioxide. And when I do that, I end up with 0.0507 moles. Remember, it's always a good rule to keep 3 sig figs in these mole table or in the BCA tables in order for things to come out properly. All right, so to determine the amount of oxygen we would need to double this amount. So we take this up. Remember, we're going to take it up. We're going to divide by whatever coefficient is here. So we're going to divide by 1. We're going to put that up into our cloud. And then when we come back down, we multiply. So coming back down, we're going to multiply by 2. And that means that we're going to need 0.1014 moles, or we're going to need for that many moles of oxygen to start with. But they didn't want to know moles of oxygen. They wanted to know grams. So we're going to take that and we're going to multiply it by 32, because this is a Brinkelhoff, so 32. And when we do that, we end up with 3.24 grams of oxygen needed. Okay. They also wanted to know here the mass of water produced when 34 grams of methane is burned. We are now going to start with 34 grams of methane. So I need to multiply this by 16, divide this by 16. That'll give me my moles of methane. So 34 divided by 16 is 2.125 moles of methane, and I'm going to double that because I'm going to take this up into the cloud. I'm going to divide by 1. When I bring it down back out of the cloud, I need to multiply by 2. So that's I'm going to produce 4.25 moles of water. If I take my 4.25 moles of water and I multiply it by 18, that's going to give me 76.5 grams of water produced. Okay, let's look at our next problem here. Experiment, we're going to be reacting a ratio of moles between metal X and bromine. It's found that 4 grams of bromine react with 1 gram of X, and the X has a molar mass of 40. Calculate the molar ratio and the chemical equation then. So when we do that, we've got our bromine here. Remember, bromine is a Brinkelhoff. So if I divide my 4 grams by 79.9 times 2, so I'm going to divide 4 divided by 159.8. That's going to give me 0.2503 moles of bromine. There we go. And if I have that, I also had 1 gram here of this. If I divide that by 40, so X equals, how many moles is that? 1 divided by 40. I end up with the same amount, 0.025. So it's a 1-to-1 ratio. So it would be XBR. And if we look at our periodic table and find remember this is going to be a +1, this is because this is a -1. That means that I'm dealing with an alkali metal here, and the alkali metal that has a molar mass of 40 is going to be potassium. Okay. All right. Here we have we want to prepare a 275 milliliter, 1.2 molar solution of sodium carbonate. And they want to know what the mass of the sodium carbonate is that we need to start with. So this is my molarity. 1.2 equals X over 275, but it's 0.275 because remember your volume has to be in liters when you're working with molarity. So 1.2 times 0.275, that's going to give me X equals 0.33 moles of sodium carbonate. And then I need to turn that into grams. So I'm going to multiply by the molar mass of sodium carbonate, which ends up being 106. So when I do that, that's 35.0 grams of sodium carbonate. Our next problem, we're working with copper sulfate pentahydrate. It has a mass of 8.512. It's dissolved in 500 mils of water. A 25 mil portion sample reacts with 20 mils of 17.1702 moles molar iodide ions, and they want to know the molar ratio of the copper 2 ions to the iodine ions in the reaction. So if we look at this, our copper sulfate pentahydrate, if we take that and we take the mass of it and we divide by the molar mass for copper sulfate pentahydrate, I end up with 0.0341 moles of copper sulfate pentahydrate. And my iodine, so I have my copper here. Because this is in a 1-to-1 ratio, that means that I'm going to have the same number of copper ions here. So my copper 2 ions, I'm going to have 0.0341 moles of that. And then my iodine here, I had, if I want to figure out those, I'm going to have my molarity, which is 0.1702 equals X over, and we had a 25 mil portion, so that's 0.025 liters. And so if I multiply those together, I end up with 0.0682 moles of iodine. So that means that I've got this in a 1-to-2 ratio. So it would be CuI2 would be the formula for this. So in this reaction, we have carbonate in antacid tablets, and it's going to be neutralizing stomach acid. We have 25 milliliters of 0.1 molar sodium carbonate solution, and it's going to react with 35.3 milliliters of hydrochloric. They want to know what the molarity of this hydrochloric acid is. So if we look at this equation, we have our sodium carbonate. We have it reacting with our hydrochloric acid, and it's going to form water. It's going to form carbon dioxide, and it will also form sodium chloride. So when we're looking at this, this is our gas that's forming. We're forming liquid water here. We do need to balance this equation, so we need to put a 2 here and a 2 here, and that should get it to come into balance. Yes. Okay. So now that we have that balanced, we can look and see how many moles of this material we have. Well, if we have a 0.1 molar equals X over 0.025 for the 25 milliliters here. If we solve for X, X is going to equal, let's grab a calculator here. I believe it's 0.0025. So 0.025 times 0.1, and yes, it is indeed 0.0025 molar. And then for that, we need to then take this amount. We're going to put it up into the cloud and bring it back down. So that means that we need 0.0050 of our hydrochloric. And if we take that divided by 0.0353, so we had this many moles formed, so 0.0050 moles divided by 0.0353 liters, and that's going to give us a molarity of 0.142 molar, and that would be HCl. Our next problem, we're going to be looking at zinc metal and it reacting with sulfuric acid. So let's go and put down what our reaction looks like, make sure that our equation is balanced. When this happens, this is a single replacement reaction where our zinc will go with our sulfate, forming zinc sulfate, and we'll be giving off hydrogen gas. Equation's balanced, so we're ready to go ahead and start. We need to figure out our moles of sulfuric acid. So we have 0.2 molar sulfuric acid, and we've got 75 milliliters of that. So remember, our molarity equals our moles, which is what we're solving for, over our liters of solution. So we need to put that in liters. So when we do that, our moles of sulfuric acid that we're starting with is 0.015. That means that if we start with 0.015 of this, we're going to need 0.015 of this since our coefficients are in a 1-to-1 ratio. So if we have 0.015 moles of zinc, and we need to know the mass of that, we simply take that and multiply that by the mass off the periodic table, because in 1 mole there is 65.4 grams of zinc. Multiply that out and you end up with 0.981 grams of zinc needed. All right, hydroxides then can be used to neutralize acids. They want to know what volume of a 1 molar NaOH would need to be available to neutralize 25 mils of 2 molar solution here. We have NaOH. We have it reacting with HCl. That's going to form water. And it's also going to form NaCl. So this is a neutralization reaction. Our reaction is already balanced here, so we don't need to balance that. We do need to figure out how many moles of HCl we're starting with. So if we have 2 molar equals moles of HCl over 0.025. So when we multiply that out, we end up with, and this is HCl, so 0.05 moles of HCl. So this is a 1-to-1 ratio. So I would need 0.05 moles of NaOH. And if I have that, They want to know a 1 molar solution, so 0.05 moles of NaOH over X liters equals 1 molar NaOH. So if I multiply that out and divide, that means that I'm going to need 0.05 liters, which equals, they didn't say specifically what units they wanted those in, but that would also be 50 milliliters if they asked for milliliters. So molar volume can also be used, and we can use gas stoichiometry. You learned back in, I believe it was Unit 3, about our ideal gas law, where we can find out information with standard amounts of moles, and we're able to then do calculations with that. So in your BCA tables that we had set up here earlier, you were able to use moles in here. You can also use liters of gas in there as well, because remember that the identity of a gas, it's irrelevant, because in 1 mole we have 22.4 liters of ideal gas. Okay, so we're going to assume as standard conditions and temperature, and if we do that, we don't have to we can work easily with our information here. So number 1 here is calculate the mass of ammonium chloride required to produce 11.6 liters of ammonia gas with this reaction. Okay. So when we go through this, we've got the reaction already done. Calculate the mass of ammonium chloride required to produce this much ammonium gas. So if mass of ammonium chloride, so we're trying to find out the mass of this. And we want to produce 11.6 liters of this gas in the process. So if we do that, we can go back and we can calculate how many moles there are of this gas here. Okay, so we need to figure out our moles of this gas. So we put that into our PV equals nRT formula. Our pressure, it said standard temperature and pressure, so our pressure we would use is 1. We've got 11.6 here. Our N value is what we're solving for. Our R value is going to be 0.08201. Sorry, 0.0820. Look that up just real quick. 206, sorry, 206. And our temperature is 273 because it said standard temperature. All right, so when we do that, we can solve for N here, and N ends up being 0.518 moles. And that is going to be our NH3. Okay, so if we have 0.518 moles of this, that means that we had to start, since this isn't a 1-to-1 ratio or a 2-to-2 ratio, we had to start with 0.518 moles of the sodium or ammonium chloride. So they wanted to know, they didn't want to know necessarily moles, they wanted to know grams. And so if we take that and we multiply by the molar mass of ammonium chloride, then we are able to determine what our value is for that. So let's find the mass of ammonium chloride here. We have a 18 plus 35.5. That ends up being 53.8 grams per 1 mole. And when we multiply that out, we end up with 27.7 grams of NH4Cl. That's how much we would need to start with. The next one is we're going to calculate the volume of CO2 produced when 9.8 grams of barium carbonate is decomposed. So we're going to start here. If we start out this problem where we determine the number of moles, so we're going to divide this by the molar mass. When we do that, we end up with 0.0499 for our moles. This is in a 1-to-1 ratio. So we're calculating the volume of CO2. So that's going to be 0.0499 moles of CO2 produced. Then we're able to, under standard temperature and pressure, we can put that information into this equation. We are calculating volume, so we're going to divide both sides by P. And so our volume is going to equal our 0.0499 times 0.08206 times 273. And we're going to divide that by our pressure, which is 1. And when we do that, our answer comes out to be 1.12 liters. And that's liters of CO2. And that's your final answer. Here we are calculating our molar mass of this gas. Remember that your molar mass equals moles over, I'm sorry, let me start that over. Sorry. Molar mass equals grams over moles. So if we wanted to solve for molar mass, we could simply we could get rid of our moles here, because we could say, okay, our moles equals grams over molar mass. So now in place of our moles and our PV equals in our T formula, we can replace this N with this and then solve for molar mass. So if PV equals grams RT over molar mass, we want to get molar mass by itself. So molar mass PV equals grams times RT. So molar mass is going to equal grams RT over PV. So our molar mass, now we'll start subbing in information here, is going to equal our grams here. So we have 0.120 grams. We're going to multiply that by our R value here, which is 0.08206. We're going to multiply that by our temperature, but remember the temperature has to be in Kelvin. So if I add 273 to that, I end up with 323. Then I'm going to divide that by my pressure, and they gave us a standard, I guess this would be standard pressure here. I guess our temperature wasn't, but our pressure was. So 1 here. And then we're going to multiply that times this value, but remember that has to be in liters, so 0.0380. When we do that, we end up with a molar mass equal to 83.7, and that's going to be grams per mole, and that is your final answer. The next one we have here, we're dealing with sulfur and chlorine. We're reacting. We're going to form sulfur. I guess this would be sulfur hexachloride. So we have 202 grams of sulfur. They're reacting with 303 grams of chlorine, which is a limiting reactant. What's the mass of the product, and what's the excess reactant that will be left over? So this is a perfect equation for our BCA tables. Let's start that over again so I have a little bit more room here. All right, so sulfur, I've got 3Cl2, and I have SCl. This is going to be my BCA table. So to start with, I don't have anything here. Here I am going to start with 202, so I'm going to divide this by 32.1. That's going to give me 6.29 moles of sulfur. I am going to, remember this is a Bringelhoff, so I need to divide this by 71.0, and that's going to give me 4.27 grams of this. So remember how we brought these up into the cloud last year when we did these problems? This divided by 1 is still going to be 6.29. This I have to divide by 3 though. So 4.27 divided by 3 ends up being 1.42. Okay. And then that's what I have to look at these two clouds. Which one is the smallest? I get rid of the other one, and then I'm going to use this for my calculation. So I'm going to bring this down out of the cloud. This is going to be 1.42. This I'm going to multiply times 3. I'm going to use up 4.27. I'm going to have 0 left over here. And here, when I bring this down out of the cloud, again, I multiply by 1. I end up with 1.42. I subtract these values. So I end up with 4.87 moles left over. I'm going to take that okay, they wanted us actually to tell them what the limiting reactant was. The limiting reactant was the chlorine here. The mass of the product produced, we need to take the 1.42. We need to multiply that by the molar mass of sulfur chloride, which is 32.1 plus 35.5. That's 67.6. And that's grams per mole. When I do that, I end up with 96.0 grams. And that is SCl that is formed. They wanted to know the mass of the excess reactants left over, so I have 4.87 moles of S. I'm going to multiply that by 32.1 grams per 1 mole. And when I do that, I end up with 156.3 grams of sulfur. And that's how much I had excess. So as you saw in the last problem, the limiting reactant is what we're going to run out of before we can finish all of our reactions or finish using all of the reactants up. So that's what limits us from producing any more products. Percent yield then is the actual yield of the product divided by how much we should theoretically get. This theoretical yield is always what we calculate in our BCA tables. Do not confuse percent yield with percent error. So percent yield is actual over theoretical, and we don't subtract, we don't do any of that stuff. The actual amount should be less than your theoretical amount. So we're going to do a percent yield problem here. We know that we're starting with 23.4 grams of aluminum. We have excess oxygen, so they've already taken care of trying to figure out our limiting reactant. That's already been done. That's going to be our aluminum. And they're telling us how much is formed. This is how much is actually formed experimentally. We want to figure out theory how much we should have formed. So we're going to take our equation up here. We're going to convert this into moles first. So once we convert that into moles by dividing it by 27, which is the mass off the periodic table, we end up with 0.867 moles of this. If I divide that by 4 and then multiply it by 2, that will give me 0.433 moles of aluminum oxide. If I take the 0.433 and I multiply by the mass of aluminum oxide, that's going to give me 44.2 grams. Now that's how much I should make theoretically. In reality, we made 39.3 grams. So 39.3 grams, we're going to multiply that by 100, and that's going to give us our percent yield, which is 88.9%. So hopefully you got that answer. All right, the next thing that we're going to talk about is a combustion reaction. And these can get a little tricky. They're going to tell you about the moles of CO2. They might give you that. They might give you the moles of hydrogen that were used, and then you have to go back and try to figure out the oxygen. And so it can be a little tricky, because what they're going to do is they're going to eventually lead you to be able to figure out what the formula for the hydrocarbon was. Okay, so we've got this guy, and he is being analyzed by combustion. We find that 0.33 grams is producing 0.579 grams of carbon dioxide and 0.142 grams of water. The acid contains only carbon, hydrogen, and oxygen, and they want to know what the empirical formula is for that. So if I look at that, I know that I have, for my CO2, I have 0.579 grams. And for my water, I have 0.142 grams. So when I look at this, I can do a percent comp for this material, because I know that 27.3% of the mass of this formula, because I can do, remember how we did this when we were in regular chem, we had 2 times 16, and we had 1 times 12, and we add, we multiply those together, so 12.0, and this would have been 32.0, and then add that together, that's 44.0, and if we divide this by 44, and divide this by 44, that's going to tell us that our percent carbon here is 27.3% carbon. So if I take this mass here, 0.579, and I multiply that by 0.273, that's going to tell me my grams of carbon. And when I do that, I end up with 0.158 grams of carbon. And then we can't really do that for, well, we can do that for the water, and we can't do it for the oxygen in the water, but we can do it for the hydrogen here, okay? Because we had oxygen that was part of our, remember, we have this CHO plus O2 yields CO2 plus H2O. We've got this oxygen that came in here, and we've got oxygen here. So we can't figure out like how much oxygen is in this yet until we figure out the hydrogen here. But if we do the same thing here with water, we end up with our hydrogen being 11.1% hydrogen. So if I take 0.142 times 11 point, or I'm sorry, take that out of percent form. So 0.142 times 0.111, I end up with my hydrogen being 0.05158 grams of hydrogen. Now, we know that we started out with this as our total amount. So if we know the amount of carbon in it and we know the amount of hydrogen, all we have to do is subtract to get the amount of oxygen. So if I take 0.3 minus my 0.0158 for my hydrogen minus my 0.158 for my carbon, that's going to leave me with 0.126 grams of oxygen. And so what I can do is I can convert those into moles. So we're going to convert, I'm just going to try to get some space here to do the next steps. If we take our carbon and we convert that into moles, I'm going to end up with 0.0132 moles of carbon. I'm going to end up with 0.0158 moles of hydrogen, and I will end up with 0.0076 0.788 moles of oxygen. And remember how we do these empirical formulas? We're going to divide by the lowest mole amount, which happens to be our oxygen. This, of course, divided by itself would be 1. This ends up being 6. No, I'm sorry. This ends up being 2. My apologies. And this ends up being 1.67. So here we've got kind of a sticky situation where we don't have whole numbers, and you can't have these decimal numbers in your equations. So we're going to multiply everything here by 3. So this will end up being 5, this ends up being 6, and this ends up being 3. So our formula that we end up with for our answer is going to be C5H6O3. And that'll be our answer for this one. All right, the next one we're working with, we've got hydrates here. Our hydrate is a situation where we have a molecule, and essentially kind of an analogy. We've essentially got water molecules that are kind of velcroed on, so they're kind of stuck on. But if you heat it enough, you can actually drive that water off, and then you can figure out by the mass difference how many water molecules were associated with that. So that's what we're going to do in our next problem here, is we're going to take cobalt chloride. We have a mass of 11.73 grams. They're going to heat that, and eventually this is the mass of the material. So we can subtract this from this, and that will give us the mass of our water. So the mass of our water here, and then we divide that by 18, that will give us the moles of water. That ends up being 2956 moles of water. So again, to get this value, what I did was I subtracted 6.41 from 11.73. That gave me my grams of water. And then I divided that by 18, which is the molar mass of water. That gave me my moles of water. I'm then going to divide that by my moles of CoCl3. So if I take this and I divide it by the molar mass of CoCl3, that ends up being 0.0493 moles. And when I do that, I end up with 6. So my formula for this would be CoCl2 6 H2O. And what that means is for every molecule of cobalt chloride that we have 6 water molecules kind of stuck to that. So if this was our molecule, we'd have 6 water molecules stuck on to that cobalt chloride molecule. If we heat that, then the water goes off into the air, and the cobalt chloride is left behind. Okay?